this is copper oxide, iron oxide, aluminum oxide, titanium oxide, zinc oxide. CuO means copper oxide, iron oxide, aluminum oxide, titanium oxide, zinc oxide. And other kinds of inorganic nanomaterials is like this: quantum dots and cadmium, selenium, zinc sulfide, like that. There are another class of nanomaterial, that is hybrid nanomaterial. Organics, organic inorganic, inorganic inorganic. That means hybrid materials can be the combination of the same organic nanomaterial, or inorganic and inorganic nanomaterial, or organic and inorganic nanomaterial. So this combination can be called as hybrid nanomaterials. In hybrid nanomaterial, you can use carbon nanotubes with metal oxide semiconductors, like that. Yeah, coming about the classification of nanomaterials, a mixed metal oxide nanocomposites is a solid material containing two or more phases, where one of the phases has the dimensions less than 100 nanometers. The first is mixed oxide nanocomposite, in which mixed oxides form solid solutions such as TiO2, SnO2 nanocomposite. If you observe these two, this is inorganic nanomaterial, this is also inorganic nanomaterial. So this, by using these two different two inorganic nanomaterials, we can make a nanocomposite. The second category fall those mixed oxides that form distinct chemical compounds. Like that, the third is systems that form neither compound nor solid solutions. That means nanomaterial can be a solid, or it can be a liquid. Some nanomaterials, we can prepare the same material in liquid phase, and we can prepare the same material in solid state. So depends on the requirement of our application, we need to choose, or we need to decide whether our nanomaterial must be in solid form or our nanomaterial must be in liquid form. So depends on the application of the material, we need to choose the state or the form of nanomaterial. Finally, there are those systems that form core shell nanocomposite structures. Actually, they depends on the morphology. We have different kinds of morphology of nanomaterials. Out of different kinds of nanomaterials, it is one of the morphology, that is core shell nanocomposite. That means one material can be treated as core, and which was covered by other material like shell, and such kind of nanomaterials are called as core shell nanocomposites. Yeah, here you can see based on the dimension or based on the morphology, you can you can able to classify the nanomaterials. Nanomaterials can be classified as per the size and dimensions. There are four types of nanomaterials, such as 0 dimension, 1 dimension, 2 dimension, and 3 dimension. How can we classify? If you look this, these particles, these spherical like particles can be called as 0 dimensional nanomaterial. For example, like carbon nanotube, if any material with below 100 nanometer, it is in the formation of wire or rod, you can call them as one dimensional nanomaterial. The basic requirement for any kind of nanomaterial is, we already discussed, that is one dimension should be less than 100 nanometer, then it can be called as nanomaterial. So here are 0 dimensional materials, 1 dimensional material, two-dimensional material and this is three-dimensional material. So if it has some planar structure. For example, if you take a sheet like a paper, so with below 100 nanometer, it can be treated as two-dimensional nanomaterial. And this is a cube. So any kind of cubical structure, that means like a flower can be a flower below 100 nanometer size, it can be called as a three-dimensional nanomaterial. Here you can observe some structures related to the zero-dimensional, one-dimensional, two-dimensional, three-dimensional. All the quantum dots can be treated as zero-dimensional material, and for example some nanofibers, nanorods, nanowires, these are all can be called as one-dimensional material. If you see this image, you can see a rod-like or a wire-like structure. So these are called nanofibers or some other nanowires, nanorods. These are all comes under the category of one-dimensional nanomaterials. Like for example, so if your nanomaterial, like for example graphene oxide, it has a layered structure. Its layers are in nano size. So all the multi layers. So the best example for two-dimensional material is graphene oxide. So as you know, graphene oxide is a wonderful material in a nanoscience and nanotechnology, which finds different kinds of applications in many fields. And like this, so if a material has number of layers, you can also treat it as three-dimensional material. So flowers, nanoflowers comes under the category of three-dimensional material. So based on the morphology, we can classify the nanomaterials under zero-dimensional materials, one-dimensional material, two-dimensional, and finally three-dimensional materials. Yeah. Now we will discuss in details of the classification of nanomaterial. Yeah, first one is zero-dimensional nanomaterial. In zero-dimensional nanomaterial, you can see here 0D. D means dimension. Zero-dimensional nanomaterials. All the dimensions of materials exist in nanoscale. For example, all the nanoparticles, you might heard about gold nanoparticles, palladium nanoparticles, platinum nanoparticles, silver nanoparticles, or some kinds of quantum dots. So these are all in spherical structure, that is zero-dimensional. So nanoparticles can be spherical in size with a diameter of 1 to 100 nanometer. So below 100 nanometer, a spherical structure materials can be called as zero-dimensional materials. So it is very important. You can observe mostly gold nanoparticles. You might heard about gold nanoparticles, which plays a major role in many kinds of applications. These are fullerenes made with carbon atoms, and it is quantum dot. So for zero-dimensional materials, the electrons are fully confined. That means you can able to observe all the atoms in this size, in this shape. So zero-dimensional nanomaterial is simply, you can imagine looks like spherical nanoparticles. So most of the nanoparticles comes under zero-dimensional nanomaterial. And what are the applications of zero-dimensional nanomaterial? In zero-dimensional nanomaterials like quantum dots has been extensively studied in light emitting diodes, LEDs, solar cells, sensors, single electron transistors, and lasers. You can observe so many applications of the zero-dimensional applications, from the point of solar cells to sensors, transistors, LEDs, lasers. So there are numerous applications of zero-dimensional nanomaterials. And the second classification of nanomaterials is one-dimensional nanomaterials. In most of my research work also, I use it to prepare CDS nanorods which can be called as one-dimensional nanomaterial. Okay, coming to the one-dimensional nanomaterial point of view, these nanomaterials having two dimensions are in the nanometer range, and other one is remain in bulk state. So two dimensions must be in less than 100 nanometers, then you can treat as a one-dimensional nanomaterial. Nano wires, nano fibers, nano rods, nano tubes are examples of one-dimensional nanomaterials. Some metals like gold, silver, silicon, etc., and also some metal oxides, zinc oxide, titanium oxide, cerium oxide, etc. So these materials we can prepare one-dimensional nanomaterials. In one-dimensional and two-dimensional materials, electron confinement and delocalization coexist. We will discuss this in detail in our future classes. What is electron confinement, what is delocalization, coexist, like that. So, and coming, what are the advantages of one-dimensional materials? These one-dimensional nanostructures provide unique properties such as high electron mobility or quantum confinement effects. And also one-dimensional materials have very high specific surface area, they show very high mechanical strength. Examples: nanowires, nanorods, and nanotubes. These kinds of nanomaterials have high surface area and mechanical strength, which can be used in supercapacitors and also in many energy related applications like solar cells, photocatalysis, and many energy related applications. So this is the one type of classification. And the third is two-dimensional. In this class of nanomaterials, one dimension is reduced to nanometer range and the other two dimensions remains bulk. Examples: nano thin films, thin film multi-layers, nano sheets or nano walls are two-dimensional nanomaterials. The area of 2D nanomaterials can be several square micrometers, keeping thickness always in the nanoscale range. In one-dimensional and two-dimensional nanomaterials, electron confinement and delocalization coexist. In two-dimensional material, you can simply, if you consider a paper, it is a two-dimensional material. So this, like graphene oxide, you can observe two-dimensional nanomaterial. And coming to the three-dimensional nanomaterials, there are no dimensions in nano scale and all the dimensions are in macro scale. Bulk materials are 3D nanomaterials that are composed of individual blocks which may be in nanometer scale. For 3D nanomaterials, the electrons are fully delocalized. So three-dimensional materials also have more advantages of like this. So that means three-dimensional material having number of small one-dimensional or number of zero-dimensional materials. So if more zero-dimensional materials combined together, it can form a three-dimensional structure. The advantage of three-dimensional nanostructured photoelectrodes are effective light harvesting, charge transport, and collection. Every kind of nanomaterial, that means zero-dimensional, one-dimensional, two-dimensional, and three-dimensional, every dimensional material has its own importance in terms of applications. So there are, finally we can say nanomaterials can be classified into based on the morphology into zero dimensional, example quantum dots nanoparticles, coming to one dimensional nanomaterial, example nanorods, nanowires, etc., and three dimensional, two dimensional, it is example graphene oxide, three dimensional. So it has its own importance to perform high performance of nanomaterials. Yeah, coming to the properties of nanomaterials, mechanical properties. We'll see the how the mechanical properties will change in nanomaterials, and the nanomaterials have less defects compared to bulk materials, which increase the mechanical strength. Strength of any material is very important in case of mechanical properties, uh, but in case of nanomaterials we can find less defects, so which will give high strength. So in when compared to bulk materials, nanomaterials have high strength. Mechanical properties of nanomaterials which are higher 2 times magnitude than that of bulk form. Examples: nanocrystalline carbides are much stronger, harder, and wear resistant. It can be used in micro drills. So because of the strength of nanomaterials, it can find many mechanical properties. And the second example is carbon nanotubes used in bats, rockets of due to their strength. So because of this, carbon nanotubes can be used in many sports where because it has a high strength. So simply in the field of mechanical properties, nanomaterials are extremely important because the nanomaterials can have higher strength. Electric properties. Electric properties also majorly changes when a material comes from bulk form to nano form. Electrical conductivity decreases with a reduced dimension due to increased surface scattering and widening of band gap. You know, band gap is the gap between valence band and conduction band. So the gap between valence band and conduction band is known as band gap, and this band gap is very important in electrical properties and optical properties. Based on the morphology and based on the dimensionality and based on the different kinds of materials, band gap of nanomaterial will change, and this tuning or this band gap is very important. If you see here, so this is the valence band edge and this is conduction band edge. The band edge between valence band edge and conduction band edge is called a band gap. So this band gap will changes, this band gap will change due to the size of nanoparticles. For example, as here you can see, some metal nanowires undergo transition to become semiconductor, and semiconductor might become insulator when their diameter are reduced below critical diameters. That means depends on the or based on the band gap, so a metal nanowire can become semiconductor and a semiconductor might become insulator, depends on the diameter of the particular nano material. This band gap is very important to capture the sunlight. Our course is energy related applications, and the energy absorbed by the nanomaterial from the sun or from any kind of visible light, band gap is very very important. Some kind of materials which is near to 2.4 electron volt, like that, so there is a tunability of band gap. Some materials can capture more light and some materials cannot capture more light. For example, if you see some kinds ultraviolet materials, some are visible active materials. That means some materials, for example like zinc oxide and tin oxide, they can absorb only ultraviolet light from the electromagnetic spectrum or from the sunlight, because it has more band gap. That means more band gap materials cannot absorb all the light from the sun. Likewise, some visible active materials, it can attract more light because of the small band gap. So the tuning of band gap is very very important in energy related applications. So by changing band gap or by changing the widening of band gap, we can tune the optical and electrical properties as per the requirement of the application. For example, in kinds of solar cell, like solar cells and sensors, we need an optimized band gap. Magnetic properties. Magnetic properties are a class of nanoparticles which can be manipulated using magnetic field. The magnetic moment of nanoparticles is found to be very less as compared to bulk size. Ferromagnetism disappears and transfers to superparamagnetism in the nanometer scale due to the huge surface energy. That means when a material comes to nanoscale from bulk size, its magnetic property will change. Some will change from ferromagnetism to paramagnetism, and some will change paramagnetism to ferromagnetism. For example, commonly consists of magnetic elements such as iron, nickel, cobalt and their compounds from 1 to 100 nanometers. Performance is usually the best performance we can observe in range of 10 to 20 nanometer for various kinds of magnetic applications. So these are the some of the magnetic elements, so which by using we can make cobalt oxide, nickel oxide, iron oxide, and the combinations of different magnetic elements we can make magnetic materials. But all the magnetic properties will change when it comes from bulk stage to nano materials. It depends on the size of nanoparticles and the requirement of nanomaterials. And this is one of the important properties of nanomaterials: surface Plasmon resonance. It can be simply termed as SPR. So this is the special property which was exhibited by metals mostly. When the size of nanocrystal is smaller than de Broglie wavelength, surface Plasmon resonance is the demonstration of a resonance effect due to the interaction of conduction electrons of metal nanoparticles with incident photons. This property can be observed mainly in metals like gold, silver and copper, but majorly it belongs to gold nanoparticles and silver nanoparticles, or any gold nanorods, silver nanorods, like that. Bulk gold appears yellow in color. If you see very clearly the bulk gold, so this is the bulk gold, it appears in yellow color. This is bulk gold, it looks in yellow color. But the same gold when the size of the gold particles decreases to nano size, it changes its color. It appears red, wine red, like this. And also this is the nano size. That means if you see here, the size of nanoparticle decreases, its color also changes. Majorly these are all in nano size, but this is in bulk size. In bulk size, the gold is in yellow color, but that means when the size changes, its optical properties also changed. Here it appears in yellow color, here it appears in red, pink, wine red, like that, different colors. That means its optical properties are very clearly changes with respect to the size of nanoparticles. And coming to the quantum size effect, here also the quantum size effect is different for different sizes. The reduction of materials dimension has pronounced effects on the optical properties due to the increased energy level spacing. Increased energy level spacing means it belongs to the band gap. As the band gap changes, usually when the size of nanoparticle changes, automatically the energy level spacing changes. It will tune. You can see here the energy levels are changing. Energy levels are changing. Energy band gap, this is the valence band, and this is the conduction band. The band gap is changing as the particles size changes. Here you can see from 6 nanometer to 2 nanometer, as the size of particle decreasing, the color is changing. Color means it is an optical property. So as the size changes, band gap changes, also the optical properties changes. So photograph of 5 colloidal dispersions of cadmium selenium quantum dots with different sizes under excitation with a UV lamp in the dark. So without light, all the solutions looks similar, but when you on an UV lamp, ultraviolet light, the solutions will color differently because the size of quantum dots or the size of nanoparticles are different. You can see here the color of photoluminescence changes from red to blue as the quantum dot diameter is reduced from 6 to 2 nanometer. Smaller dots emit higher energy light, that is bluer in color, whereas larger dots emit low energy red light. So depends on the size of nanoparticles, the band gap will change, automatically the optical properties will change. So optical properties of nanomaterial is very important for energy related applications because the tuning of band gap changes the optical properties. And coming to the some examples of optical properties, zinc oxide is one of the standard nanomaterial. So you can observe different properties for the same zinc oxide at large size, that means bulk, and in nanoscale sized zinc oxide nanoparticle. You can observe here, this is large zinc oxide nanoparticle, this is nano sized zinc oxide particle. You can observe this large sized or bulk zinc oxide particles cannot block the ultraviolet light, and it scatter visible light, appear white in color. But the same zinc oxide when size of the nanoparticle decreases, size of the particle decreases, that means nano-sized zinc oxide particles, it can block as UV, it can block UV light. That's why most of the sports persons use sunscreen, zinc oxide sunscreens, because it can block the UV light, so which will affect our skin from the sun. So the traditional zinc oxide sunscreen is white, but nanoscale zinc oxide sunscreen is clearer. So from this point we can confirm that large zinc oxide, that means bulk zinc oxide, cannot block the UV light, but nano sized zinc oxide block the UV light. And also the large size zinc oxide appear in white color, but the nano sized zinc oxide, you can see here, so small compared to the wavelength of visible light that they don't scatter, it appears clear. So it can, even if you use nano sized zinc oxide, so it is a clearer size, it is transparent, so you cannot able to it will disperse on the screen. So this is one of the example for optical properties. Coming to the chemical properties of nanomaterials, as particle size decreases, a greater proportion of atoms are found at the surface compared to those inside. That means nanoparticles have a much greater surface area per given volume compared with large particles. It makes materials more chemically reactive. At the first, some of the first slides we were discussed that surface area is most important for nano materials. That means why the surface area plays a major role in nanomaterial means, if surface area is more, the number of atoms is on the surface is more, which make materials more chemically reactive. That means most of the atoms involved in the reaction. That's why chemical properties will majorly change. For example, we discussed it in an earlier slide. Gold is inert at bulk scale, whereas acts as catalyst at nanoscale. In chemical reactions, like in photocatalytic reactions or in some of the chemical reactions, gold is very stable and gold is inert at bulk stage, but it is very good catalyst at a nanoscale. Physical property, melting point of a substance. Usually bulk materials melting point is different, and nanomaterials melting point is different. That means temperature at which the atoms, ions or molecules in a substance have enough energy to overcome the intermolecular forces that hold them in a fixed position in a solid. If you see here, surface atoms requires less energy to move because they are in contact with fewer atoms of the substance. That means in contact with 3 atoms. So this is contacted with 3 atoms and in contact with 7 atoms. So melting point will also change, depends on the size of the nanomaterials. In bulk materials we need more temperature, that means more energy for melting, but in nanomaterials we need less energy for the melting point of a material, because all the atoms are at surface in nanomaterial, so it can easily melt with low energy. So simply, for bulk materials we need high energy to melt a material for melting point, but in case of nanomaterial we require, or the material requires less energy. Understanding melting point, macro versus nano. See, the